Okay, take two. Welcome to the second meeting of the BunG Seminar. Today we have Nikolay Grantcharov speaking about representation theory of finite W-algebras. Thanks very much.
Okay, so to start things off, I want to recall a few constructions that Yvonne gave us last time on how to construct W-algebras using this quantization process. And then we'll discuss the main results, which are Scriabin and Harish-Chandra bimodules. So here's the setup. So G will be a semi-simple Lie algebra for the complex numbers. O is going to be a fixed nilpotent orbit. And we're going to fix nilpotent element E inside O. And you can assume that it's principal. I think most of the things I say today actually do not use this, but for safety, assume it's principal. And then by Jacobson-Morozov theorem, fix and SL2 triple corresponding to this E. And then this SL2 triple gives the following Slotoway slice S to be E plus kernel of add F. And recall that this Slotoway slice was transverse to O. And furthermore, it was also defined using Hamiltonian reduction. And this is important. So I'm going to recall its construction. Using Hamiltonian reduction. And maybe I'll also fix, so since we have semi-simple Lie algebra, I'm going to denote chi, the corresponding dual element to E. I'll denote here. So that it pairs with the killing form, with E to 1. And sometimes this chi is called a Whittaker function or Whittaker character. And another way of saying Hamiltonian reduction that you'll see in the literature is constant Whittaker reduction, corresponding to this character chi. And the nilpotent n, which I'll recall. So the add H action on G induces eigenspace decomposition. So these GIs are elements whose eigenvalue at H is I. And then so the role of the Cartan is played by this Lagrangian L inside G minus 1. So Lagrangian with respect to like this canonical form induced by the Cartan killing form. And then the role of the nilpotent is played by, so yeah, I'll use this fractor n. Losev likes to draw like a bar. I don't. So I'll try to use curly n. So this is going to be L plus direct sum over all weights less than -2. Okay, and then we apply Whittaker reduction to this. So this is L is a Lagrangian in G minus one. So this is some vector space, and you just pick a Lagrangian.
Oh, okay.
Form is E dot X, bracket X.
Yeah. So it's in the principal case, it's zero. So this very good point. This is just zero, and this is just the sum of all weights, which are let's say minus two. So it's just the usual Cartan. N is the usual node. Yeah, it's very good to keep in mind the principal case. Potent, and then so let N be this exponential. Yeah, in the principal case, only even eigenspaces survive. Okay. So for Hamiltonian reduction, you need a moment map, and this is just given by dualizing the canonical inclusion. And then the Slotoway slice is just given by taking the pre-image of chi mod n. So this quotient is taken in the sense that the coordinate function is just the n invariant functions on this pre-image. And recall this theorem by Ginzburg that n acts freely on this fiber. So there exists an isomorphism of varieties. So, i.e. So this is very important. Okay, and then using this presentation with like classical Hamiltonian reduction, we can quantize it nicely. So quantizing, which means anytime you see functions on the Lie algebra, you replace it with the enveloping algebra. So we have this W-algebra, which is enveloping algebra mod the ideal generated by the nilpotent n shifted by chi. This is called the W-algebra associated to the pair, or just to, I'll say to E. I'm going to omit the notation E from W. E is always fixed. We don't vary E. And one more notation, just since I'm going to be using this ideal, I will call it n sub chi. And I forgot to take the, sorry. You take the left invariance under N, the group. So there's always, in Whittaker reduction, there's always two steps. You reduce, so you mod out by the nilpotent, and then you take the invariance under the nilpotent. Okay, and then, so as a remark, we're not going to use this, but since Justin asked last time, you can always write with a Hamiltonian reduction using the endomorphism algebra. So you can write W as endomorphism, and this just follows from definition, like it holds in general. Not, you don't need to reduce along nilpotent. And I'm going to denote Q for quotient. So there's one more thing I want to recall, and that's the Kazhdan gradient. So this is also important. We'll see the theorem. So yeah, I guess Losev didn't actually call it Kazhdan grading anywhere, but this is sort of a twisted C star action on the Lie algebra. So we introduce modified C star action on G so that it preserves the Slotoway slice and it contracts it to a point. And let's recall what this modified, well, right, what this modified C star action is. Namely, given, yeah, I guess being a tiny bit sloppy, I want to really, yeah, since it's semi-simple, I will often forget the star, but I'll try to be mindful. So for any any vector field and a scalar, define this action by the formula t to the minus 2 add of gamma of t acting on C. Where gamma is this composite. First you map T diagonally to SL2. And then you use Jacobs and Morozov to embed SL2. Okay, so it's just some twisted C star action which preserves the Slotoway slice. And then this induces the following filtration on everything. So this is grading on polynomials via so that t acts by t to the n. And likewise, it induces an action for Slotoway slice and its quantization. So for the quantization, you consider, so, right? Great, I did. Vector fields which are in the usual end step PBW filtration, but whose eigenspace is I, respect to X, and then this gradient uses a filtration which is called Kazhdan filtration. I see you nodding your head, so you're going to answer the next question I have, which I actually don't understand. So you consider elements in the JPBW with I Kazhdan, so that I plus 2j is less than n, and I don't know why there's a 2j here. But anyway, this is the filtration. It works in the sense that you have the following very nice theorem. So theorem this gives you an isomorphism of the associated gradient of the W algebra with the functions on the Slotway slice, which respects the gradient on both sides and which respects the Poisson bracket. So we have where W is isomorphic to CS.
Uj of G and then I of that, right? Like that you were.
Thank you.
In the formula, it's add H acting on the side.
Thank you. I'm going way too quickly. Yeah, thank you. So isomorphism of graded Poisson. Sorry, I told you. Yeah. Great. Yeah, and so here there's the Kajdan gradient, and here's the Kajdan gradient as well. Okay, so that's the recap. And now we move on to new things. Questions so far? Yeah. Yeah.
Look down the gradient.
Yeah.
And use
Oh, because you have the t to the minus 2.
Yeah, let's see that.
Yeah, yeah, thank you. Okay. Perfect. Okay, I'm happy. Somehow I refuse to take like 30 seconds to think about this. Okay, so let's discuss Scriabin. Okay, so this is a funny story of how I learned about the proof of this. The original proof by Scriabin is like in an appendix of the author. Okay, of some paper, but this proof is like extrememely difficult. I asked Ginzburg about this, and he said it's like unreadable to him. And the way he proved it, so this proof of presenting it's in this short paper by Gahn and Ginzburg. It's like some appendix, and he said some seminar finished like 10 minutes early. He went to his office, wrote up the proof, and submitted it like the same day. It's like he just realized last minute that his main results like immediately imply this, and we'll see why. Okay, so let's introduce the notation. So it's an equivalence of categories relating W modules and UG modules. So let UG and chi mod be the category of U modules finitely generated for which this nilpotent acts locally finitely. And this is locally referred to as the Whittaker category. Okay, and then this Q, this quotient, is the main example of a module here. And then we're going to introduce a functor given by taking invariance.
like almost just integrability condition.
Yes.
Right? We just
Exactly. So we define this Whittaker functor on the category of UG modules for which n chi acts locally finitely, just given by taking invariance. But I'll switch. We always look at the chi twisted action. So I would write n chi up here, but the problem is n chi is not really like W-algebras, so that patient. Yeah, so we take the invariance under this chi-twisted.
It's long n.
Sorry?
Is it long n like the algebra, like Lagrange's Lagrangian subspace plus all of the degree minus 2n plus?
Oh, you're asking what n is?
Yeah, you just used an notation like eta.
Yeah, I mean, before I wrote x, but I wrote x here.
Okay.
Yeah, I had the same train of thought. Yeah, sorry. Oh! Thank you. Sorry.
Yeah, so n in eta. N
Yes.
in long
N in factor n, yes.
Yeah, so it, okay.
Thank you. Yeah, sorry. Okay. Okay, so I call it factor n.
It's supposed to be an n, not an eta.
Yeah, so in the old literature, it was always denoted by factor m, but I don't know, I cannot make the connection between m and nilpotent. Like nilpotent is always n or u for me.
Looks like notation for the levies.
Exactly, yes, now the levy is m. Okay, so yeah, now I can state the theorem. Finitely generated W modules is equivalent to this Whittaker category. And the functor on one side is given by taking invariance. And on the other side is given by sort of tensoring, which I don't want to call it localizing, but kind of is, I don't know. What's the correct phrase for this functor? Is it localized?
Everything we exchange is locally.
Anyway, so yeah, V is a W module, and then W sits inside Q as the invariance, so you can make sense of this, and then you just see this is Q itself lives inside here, we just explained, and then okay, so and just a remark before I give the proof, this is completely analogous to Cauchy-Vara's theorem in D modules setting. So on this side, it's like saying you have a D module on some ambient space X, which is supported on some subset Y. And this is like saying you have the D module on Y. And I'll give an interpretation involving D modules of the theorems slightly afterwards.
So the action on Q is adjoint, or is it like?
Yeah, UG acts on the left on UG by adjoint.
So not a regular, yeah.
Cauchy-Vara's theorem on D modules. I don't know if this is okay. On X supported on subvariety.
It is regular action, not the adjoint. You've destroyed the action on the right
Oh,
side.
sorry,
Passing
yeah.
its quotient.
Yeah,
so
yeah.
It's also not like a
It's the
locally
same-
finite G action. It's very much like a
I think it might be the case that they're actually the same in this case.
the adjoint action doesn't quite make sense, right? Because there's only an action.
Wanting out by this left ideal generated by N.
Right, so the only thing you have is the left action.
Yeah, Justin's right. It's the
It's just by left multiplications.
Yeah, but then it's a non-trivial statement that it belongs to the
Yes.
category.
it requires.
Yeah, there's something.
It is true though. Great. Okay, so let's give a proof. The way we will prove this is the same we'll prove everything, is you first prove the analogous statement for the quasi-classical picture. So you replace UG by sim G and W by the center G. And then you use some sort of argument involving spectral sequences along these touchdown filtrations to reduce to this. I'll skip that part and focus like on the quasi-classical. Okay, so let B be a W module. And later we'll see sort of there's an affine story. Let me not get into it. So this V has a filtration induced by the Kazan filtration. And on the W-algebra. And the isomorphism by Gunn and Ginzburg implies there's an isomorphism on the corresponding polynomial rings. And this is compatible with gratings on both sides. Yeah, so this Q is equal to functions on this fiber. Great. And then this directly implies the following. So the zeroth Lie algebra homology is just invariance under this quite twisted and action. Okay, so this tells you that taking n invariance of this guy, the same thing as taking n invariance of functions on n tensor GER-V, but the only n invariant functions on n is just a constant function. So this is just GER-V. Notice this shows one of the composites is an isomorphism on H0. And the way we show this equivalence is by showing like both composites are identity. And here, I don't know, we started over here. So we induced and then took invariance. Induced and then invariance. Okay, so this is identity. And then it's also true that all higher homologies vanish. I don't know, it also falls from this identity. I'll say here and I. Okay, so this shows that the functor of taking n invariance is exact on the classical level. Sorry, it's cut off. The tensor product is over W here. Yeah, and also, you need one more recipe in order to use this reducing to classical limit. Is that associated graded of a tensor product is a tensor product of associated graded. This falls again by Gunn Ginzburg. Third Q is free over here W. This is Ginzburg implies of Q tensor WV, your Q over W of so spectral sequence argument implies the statement we want in general, not just the quasi-classical. So, summary, taking an invariance of the induction, this identity functor. Now we show the other way, this identity. Questions? It remains sir W of the invariance. That's all. Okay. So we're going to show that the kernel and so the kernel is 0 and the co-kernel is 0. And both of these will follow sort of from what we have just done. Yeah, okay, so for the kernel, what we will do is say, if you take n invariants of the kernel, this equals the kernel intersected with the n invariants, and that is automatically 0. So the n invariance of E prime is 0, but that implies E prime is automatically 0 as well. So so if you use that the Whittaker functor, like it's if Whittaker of E is 0, then E is 0 on the category, on the Whittaker category. So that kernel of F is injective. And then for surjectivity, we just look at the corresponding long exact sequence. So then each one vanishes. We showed it's exact over here. And then H0 of E double prime. Well, okay, we know that here it's an isomorphism by the first part. Right? We showed that if you induce and then take invariance, it's the same thing as identity. So this is by forward direction. And then this implies this equals 0. And then again, so if the n invariance of E prime prime is 0, then E prime prime is 0 as well. And yeah, so that proves Skurjavins' theorem. Are there Any questions?
Yeah, I think you could simplify this considerably. I mean, so this first line here, the Whittaker of E prime is 0 implies E prime is 0. You're invoking something from a previous step, right?
Yeah, exactly.
This kind of conservativity. So that's once you know that, okay, you have adjoint functors, you've proved that the unit of the adjunction is the identity.
Yeah.
And then all you need to do is prove that the right adjoint is conservative, which is this statement. So that's enough.
Okay, yeah. Okay, and then, yeah, so last thing I want to do before the break is actually show, so this is proof. So I claim that the Whittaker functor is monoidal, so it respects the tensor product. The way you prove this is by this really cool proof that's only written down in this new preprint by Gannon and Ginzburg. It's actually like really cool. Like you do nothing. It just follows formally from Scriabin. Oh, okay, there's a demodule interpretation, but yeah, let me skip that. We all know. I mean, you can just make sense of the Whittaker category in terms of demodules on the flag variety. And you have this additional compatibility constraint saying that the difference between the action from the D and the action from the G equivariance, but that difference is just given by this character. That's what a Whittaker demodule is, and then both of those are equal to the Scriabin theorem, and this is by Bernstein localization. So it takes more time to write it down, but that's it. So now let's introduce Whittaker reduction. And for this, I need to introduce Harish-Chandra bimodules. And then I'll discuss how to define them for a very large set of algebras later. All right, so recall that a Harish-Chandra bimodule for UG A is such that we actually don't need to define that to prove monoidality. Let me introduce Harish-Chandra after the break. Yeah, okay, so I'll say, given a UG bimodule, define the Whittaker reduction. By this composite of taking an invariance and n co-invariance. This will be denoted by kappa. So take the co-invariance and then the invariance. And let me spell out explicitly how fractor n acts. So for n inside fractor n and x inside this quotient, this covariance, we define this action to be given by taking add n x plus twisting. Yeah, and then this add n becomes just a regular left n action because you're modding out by right head. So like add n you have like n times x minus x times n, but the x times n dies up to a twist.
Phi of n x doesn't die, it becomes.
Okay, up to some, yeah, okay, so up to some scalar. Okay, you're right. Yeah, so just recall applying Whittaker reduction to the enveloping algebra. I mean, this is how we define the W algebra. The principle. Okay, so let's prove monoidality. It's going to be a module over the center, or it's going to be a W bimodule. Somehow, since we defined the W algebra via Hamiltonian reduction process, like this is going to inherently have an action under this.
W is in a case, principle,
Yes,
like in a principal
yes,
case.
yes.
Right?
I don't use that though for proof I'm about to give. Theorem kappa from UG bimod to W bimod is monoidal. I'll explain what that means in the proof. And so kappa m tensor kappa m prime is kappa m tensor prime. And yeah, here the tensor product is over W, here's over UG. Great, so here's the trick. Just tensor both sides by Q. Okay, so on one hand, and look at this component and say by Scriabin that this is the same thing as taking M tensor UG. So I have Scriabin formulated anywhere. Okay, I guess we can work with this. So this is an isomorphism. Yeah, so remember kappa is invariance and co-invariance. So what you do is apply all this dagger. Here you apply dagger to, I wrote it down in my notes. Oh boy, I've lost where I've written it. I mean, it follows formally. I think you apply it to you apply it to where E is plays the role of M tensor G of Q. Yeah. Okay, so if you apply this isomorphism on this case, and you use that the n invariance of this guy is identity, so it's just Q. Or sorry, it's just M, then that's exactly what you want. So you see here, so M tensor UG of Q plays the role of E. We know that taking n invariants of this is just M. That's one composite of Scriabin. And then using that same composite, we also know that the whole thing is isomorphism, so that's it. Yeah. Formally from that, now you can use this associativity. This is the same thing as UG Q tensor kappa of M prime. So I've done nothing. Then again, Scriabin. And let you rewrite this as M tensor M prime tensor with so we've moved Q to the other side and killed the kappa. Okay, now take n invariants. N invariants, again by Scriabin, kills the Q. So n invariants of Q tensor W of anything's identity. N invariance is just the left-hand side. And then n invariance of the right-hand side, well, same thing. It's identity. Like Q tensor UG of anything, and then invariance is identity, again by Scriabin. So you have this guy is just kappa M tensor. This guy is just M. And that's the formal consequence of Scriabin. And yeah, this proof, of course, you don't need to, I mean, it used nothing special about UG or W. Sort of can hold them much greater. Okay, so I think we can take like a 5-minute break and go to Harish-Chandra. Okay, so now we can discuss Harish-Chandra bimodules. And yeah, so the reason we're going to introduce that is to show that kappa restricted to this subcategory of Harish-Chandra bimodules, and then kappa is exact. So definition. So let's first recall what it means for an ordinary UG bimodule. So a finitely generated UG bimodule K, for which the adjoint G action is locally finite is a Harish-Chandra bimodule. So sort of we got rid of the group action by imposing this algebra action being locally finite. So in the setting of W-algebras, there is no group. And then for M coherent or finitely generated D module, and anything, it has a good filtration, which I will not recall what it means. Some filtration satisfying mild hypotheses.
Kind of with like the order filtration on differential operators.
Yes. Okay, and then we define the characteristic variety support with respect to this filtration, this good filtration. this, we can sort of upgrade the notion of Harish-Chandra bimodule for it's an arbitrary pair. So given a pair B and B prime of non-negatively filtered associative algebras whose associated graded are equal, say A is a weak Harish-Chandra bimodule
It will be bimodal, right?
I don't know where my hand is going. Thank you. If its support is on the diagonal, we'll exercise this condition is automatically met for UG, Harish-Chandra UG bisection.
Spec of Gerby times.
Yeah, absolutely. Thank you.
Spec of the tensor product.
Anything else? Okay. So heading is Harish-Chandra UG bimod if and only if the associated bmod given by balance and burst and localization on the flag variety has, so I'm going to say this without defining it, has regular singularities. Reference is Kashiwara and Kawai. Definition 1.1. Okay, but what I will use is that this is also equivalent to the existence of a good filtration, which is reduced. And it's this last criteria which allows us to define Harish-Chandra W bimodules. But this is something that Ginzburg had been. Please.
Okay. So when you localize onto the flag variety, you just fix like the G actions arbitrarily and then localize. Right. So
Isn't there some formulation of BV which involves Harish-Chandra bimodules?
localize onto G mod B times G mod B or something like that.
Ooh. I think that is what I wanted.
I mean, somehow because the
Think
difference.
of it as like G weak invariant.
Fix one of the actions and localize it because the difference is.
Also, there's some central character that probably.
That was the other thing. Yeah, exactly. Really, there's some restriction on the central character of the bimodule, right?
That definitely, yeah, I wasn't careful with that. Yeah, there certainly is a central character restriction.
You take something with
Yeah.
singular central character, for example, you can just kill it.
Yeah. I don't know how to modify it, but yeah, so you have to say for some central reduction of UG.
Probably if you assume like trivial generalized central character sides, then it's fine.
Okay.
Sorry, what is reduced? So the idea, the ideal, the difference
Yeah.
should be radical.
Yeah, yeah. Yeah, okay, and yeah, so just say this is the definition. A weak Harish-Chandra W bimod is Harish-Chandra if corresponding bmod has good filtration, which is reduced, and in many cases it does due to Benson Bernstein localization. So yeah, the reference for this is 6.5.2. Ginzburg's paper on Harish-Chandra bimodules. Okay, so main theorem.
What is corresponding T1?
Oh. I skipped. Yeah, okay, so Square-Robin allows you to go from W modules to UG modules, and then use BB localization to go to D modules on the flag variety. So this is a D module on the flag variety, which is the composition of those two functors.
So those I would expect to like almost never have regular singularities, right?
Ooh, I'm not an expert. Why?
It's the Whittaker thing. So if I take like this Whittaker generator guy, this Q, and localize it onto the flag variety, I mean, again, you have to say something about central characters, but like, let's say I think first I want to kind of mod out by the augmentation ideal and force it to have a trivial central character, and then localize that. I should get exactly this kind of like Whittaker sheaf on the big cell. So it looks like it has, in particular, it has like solutions with exponential growth. So,
On the other hand, this reduced condition.
Right.
Those two reduced are also different.
I see.
B got changed. But then what's B down there?
What's
When you say reduced, this is like with
the associated graded,
uh,
the D module, the local.
so what's B? Previously there's this like,
For both W.
why does you need to,
But it's W chi and W chi prime, like two different.
then why do you need to apply?
So that I can make sense of
So is
the character.
W non-negative? It is.
Yeah, that's important actually.
What if I just, well, yeah, so what if you just wrote this definition with that it had a good filtration for W such that
Oh, that might be equivalent. So the way it's formulated in Ginzburg's paper is using like modules, but I presume you can get rid of the D because like the two equivalences, Square-Robin and BB.
that in this, how to connect this D module world with B comma B prime world. This definition, the two worlds are combined. That the good filtration has to be reduced. This bring implicitly.
B and B prime are UG.
The place
Central reduction.
got used is in the definition of weak Harish-Chandra W bimodule.
This is actually
Yeah, it's either they're both UG central reduction both sides or WW central reduction both sides.
definition is W.
Yeah. Yeah, here's WW, here's UG. Okay. So let's discuss afterwards in dinner. I do want to formulate the theorem. I don't ever use Harish-Chandra W bimodules. I just want to give the definition. Yeah, I didn't do a great job, sorry. Okay, so yeah, let's formulate this theorem precisely. So take two central characters and then define central reductions. Likewise for a W. So here I is the embedding of ZG into W. So this is a general fact that sort of the W is defined using Hamiltonian reduction along the right invariance. So the left invariance survive. And the center is like this left and right invariance. You always have an embedding of the center into the W algebra. Yeah, so we take I central. Okay. First is that there is a faithful and exact functor from the category of emit the G. Harish-Chandra bimodules onto Harish-Chandra WC prime. If you want to put weak here, you can, but it is actually a theorem that it lands in the full subcategory. And then here, I'm going to mod out by this category generated by Harish-Chandra bimodules with some support constraint. Notation N diamond to be the union of all nilpotent orbits who not contain this fixed orbit. So this is killed under the functor given by Whittaker reduction. So this functor A maps to kappa of K. So invariance and quant. Two is that sort of this Whittaker reduction only sees the easy part. It remembers very little. So the statement is that you have a nilpotent orbit is in the support of K. All right, I'll say that. If and only if its Whittaker reduction does not die. So remember, sort of, this kappa involves some N, which was constructed from O. So O depends here. And furthermore, like the support variety is equal to closure of an orbit if and only if the image of this Whittaker reduction is finite image. Yeah, so I'm going to skip most of the proof. I'm going to try to stop at 6. So the faithfulness, I didn't state the theorem. Yeah. Theorem. Claim kappa is faithful and exact. It's exact, which is the hard part. Okay, so to see that it's faithful, you can just construct an adjoint functor, which I'll say just verbally. Okay, so you can interpret kappa as taking Hom. I'm gonna get this backwards. Yeah, it's Hom into this half of k is Hom from Q to K tensor Q. And then the adjoint is just you swap the role of Q and W, and then take the finite, locally finite part of this. There's an explicit formula for the adjoint. It's in Ginzburg's paper. But let's discuss the exactness in the quasi-classical case. So what do we have to prove? So you have the following. So I'm going to slightly switch notation. And let's look at the principle. And take the Whittaker cotangent bundle. It's this Hamiltonian reduction of n along I. This is affine. And its regular functions is isomorphic to functions on G. Tensor functions on the Sloterdijk slice is affine. And you can interpret, this is sort of a claim, that Whittaker reduction is given by, so instead of UG bimodules, is SimG bimod. And then have this additional equivariance constraint. I'll say like G equivariant, GX diagonally, and then this lands in CG bimod. And this functor is given by just taking the G invariance of the pullback of M along the map G to T chi.
And then like of ZG bimodules.
ZG commutative.
That's commutative, but it's the like it's not canonically isomorphic to its own associated gradient. The associated gradient is the algebra is sim of G invariant. Right?
We have 0 over S.
Sin G.
Sin.
Yeah, so this is just another way to rewrite Whittaker reduction. The reason I wrote it this way is because then exactness is very easy to see. So first, G is reductive. Suffices to show that just the pullback, so just to show that this functor without invariance is exact. Hey, let's skip this thing. So I want to say that this is flat as a sim G module, and this falls because this map is smooth. I'll show that OT chi is a flat sim G module. This falls because this is smooth. This is proven again in a paper by Ginzburg. I'll just leave it at that. Yeah, one comment which I learned from Beer is that another way to see exactness is geometrically. So you have, okay, so there's two steps. You realize that this functor is looking at G equivariant coherent sheaves on G star. And then there's two steps. One is taking n co-invariants. And this is like restricting to the Slotaway slice. But the equivariance along the group action means that this is essentially the same as take restriction to the G-reg, the regular open part of the algebra. A restriction to a open set is exact. And then the other step of taking invariance under n, well, we know that this inequivalence, in fact, by Skrion. So nice proof this way. That's actually how I think Raskin proves the statement that affine case using these ideas. Yeah, and then the more general case, so I proved quasi-classical. Yeah, so there is really long, let me just say some of the obstacles. Okay, so you have to use good filtrations and spectral sequences. But the issue is a priori, all of the W modules have unbounded filtration from below. But is this Harish-Chandra assumption, like this assumption that it's bounded, like at Gx locally finally, which ensures that these filtrations are actually bounded below. That's one technical difficulty. Yeah, Ginzburg actually like works with like two different filtrations simultaneously. They're both good filtrations, so they both allow you to compute the spectral sequence. And like one computes one part. Yeah, it's a long technical proof. Of course, I'm going to skip it. But yeah, maybe I don't know if we can see like the affine story more. Do you have any?
I don't have anything particularly limited. And the affine story is different in also. So.
Yeah. Yeah, then let's see. Oh, great. Yeah, okay, so let me write down an application of this exactness. I think the rest of this is like survey. The application is to prove this very old conjecture by Premet on primitive ideals. So that it relates finite dimensional W modules to primitive ideals I inside G whose associated variety is the closure of the orbit. Yeah, and Losev gave a completely independent proof of this using what he calls quantum slices, which like involves looking sort of formal neighborhoods. And let me also just make a few comments. So in general, like the rep theory for finite dimensional W modules is extremely difficult. It has nothing to do with finite dimensional rep theory for UG. Like there is no Bott-Brill-Weil theory. Like your naive expectations, like, oh, you construct some line bundle on some flag variety whose global sections output dimensional reps. Like this completely fails. Like there's no such thing for W-algebras. It really involves like deep theory of like these Lustig cells, and I don't want to say anything else. And yeah, I think the only like classification known is due to Losev, and it does involve looking at quantum slices. Like that's sort of the only known approach to it. But yeah, we will not discuss finite dimensional representations. Okay, but let me sort of conclude by defining what category O looks like. So that also, it has a history, like Ginzburg was unable to find it in general, but then like Losev found this nice, clever construction, which I'll explain now. Yeah, so the main difficulty is that there's no role of a Levy. Like we saw in the principal case, like the first comment made, the Levy is just 0. So what's the role of the Levy? So we're going to let Q denote the centralizer of the SL2 triple. And in the case that is primitive, the associated Lie algebra is just 0. Keep this in mind. Q is 0 in the primitive case. But nonetheless, there's always an embedding. Oh, sorry, you mean principal? Yes. Okay, and then you pick upon inside this Lie algebra. And by the way, this Lie algebra, like it's usually like disconnected, and there's like some discrete like fact like Z mod 2 factors, but it's very like, I don't know what it looks like in general, but it's not very easy to describe. Yeah, and then set L to be the centralizer of the torus, or the Cartan inside G. And this, you can see, is the minimal Levy containing E. So again, in the principal case, centralizer of 0 is everything. So the Levy is the whole algebra. Now pick a theta inside torus such that centralizer of theta is L. And then we define the category O, which will depend on this theta. So category O of theta cis of W modules M such that 4 conditions. 1, M is finitely generated. Okay. 2 is that T acts semi-simply. 3 is that this W bigger or equal or bigger than 0 part, like this plays the role of the nilpotent. And the gradients with respect to theta this has to act locally nilpotently. And the final axiom, which is actually missing from Losev's survey article, which confused me for quite some time. Is that the T eigenspaces are finite dimensional. Or equivalently, fixed points under this W bigger than 0 part is finite dimensional. So example, E is principal implies Q is 0. Okay, 1, okay, sure, M is finite dimensional. 2 and 3 are vacuous. Good. There's nothing said. It is 0. Then 4, it just says M W bigger than 0 is finite dimensional. Well, W bigger than 0 is 0. So just saying M is finite dimensional. And compare this to the other extreme when E is 0. None of these definitions make sense. And I'll take a SL2 triple 0. But category O is like category O. So sort of in general, this whole theta is something between the two.
Sorry, so condition 2 is that the center acts diagonalizably? Sorry, what is Z?
T.
Oh, T.
Sorry.
Okay, sorry, I thought it's a T. Okay,
I'm sorry.
great.
Okay, and okay, final page. How much time is left? Okay. Great. So let me start to get some facts. We have Verma modules. So this behaves very similarly to the usual category O. And 0 is a And okay, so in Losev's notation, he says it's a module over this algebra. I will not say what this plus means, but it turns out that this is just isomorphic W0. But I did not say what W0 is. Okay. Okay, so this G, it has an eigenspace decomposition with respect to theta. And G0 is the zero eigenspace. Apply the construction of W-algebras respect to this pair, and you get W0. Yes, you have like pick a nilpotent, etc. And then, yeah, it's also true that these Vermals have unique symbol. Then yeah, let me actually explain what this W0 is a bit better, because it turns out, so the main theorem about category O is that it's related to the ordinary UG modules under so-called generalized Whittaker modules. So Scriabin was a result about W modules and Whittaker modules, and then category O is generalized Whittaker. Explain. Add theta, eigenspace L is the zero eigenspace, and then form n0 inside G0 as 4. Then this gives you W0. And then set. So everything's completely analogous, but just for completeness, I'll write it down. Then you have this twisting by central character. Okay. So the UG mod M is generalized Whittaker. Or E theta. If it's finally generated, we have diagonal action to torus. And this twisted nilpotent acts locally, nilpotently. So before, the nilpotent just acted. Yeah, okay, it's the same criteria. Okay, it's a generalized Whittaker. And yeah, so I'll stop here and formulate the main theorem to Losev. So there's an equivalence given by Whittaker reduction from this generalized Whittaker category and category O. These are these are UG modules, these are W modules. This is like a generalization of the pre-algebra flow. Okay, I'll stop here.
Questions for Nikolay? I'll ask you a question. Is I'm guessing this version of category O is Artinian.
I don't know what that means. I know it's,
Every object has finite length.
I'm not sure.
It's one of the main things that people like about usual category O. So just
I think the main like surprising thing is that it's actually semi-simple.
I mean, that's not true in the principal case. Or like in the principal case, it's just finite dimensional modules over this essentially a symmetric algebra. So definitely not.
Okay, I'll have to check. I did write in my notes it's semi-simple. Why is it not in the
Principal case, it's just finite dimensional modules over the center, right?
Yeah.
It's definitely not a semi-simple. Yeah. If the central character is required to be kind of strict, then it's doesn't make sense maybe.
okay? I think like on these central blocks, I think it's
In usual category O, we only impose generalized central character, right?
Yeah.
And then block is of finite length, and also like the lengths of the objects are kind of uniformly bounded, which would not be the case if you had this kind of picture with like it's just finite dimensional modules over the center, because then you could have arbitrary. So it does look quite nice.
yes.
Case.
Okay, I'll have to check. I was informed by Ginzburg that it's semi-simple and the proof is extremely complicated.
I see. It must be something
Central.
a little different from this thing. Okay. Any other questions? Let's thank Nikolay again.